Like that. Like the logo.
Okay, it's 3:05, so let's get started. So just a few quick announcements. Quiz 3 will be out tomorrow and due on Saturday, just like usual.
I like it.
Part 2 of homework 1 will be due next Sunday night. So how many of you actually did something of homework 1 and turned it in? Okay, so half-ish, yeah. So just make sure to do those. We highly recommend that you do so. Quiz 2 and Recitation 2 solutions are also posted on the website. So are there any questions before we get started? Yeah.
Number 4 on the homework.
Yeah.
Are we going to go over that in class, do you know?
Probably not. I already wrote up a solution for it, and I don't know if we can post them early, but we definitely will once we close the Part 2 submission. Okay. Yeah, but in all cases, you can do it with 2 states or less. Any other questions? All right, no questions, so let's get started then. So, what was the major thing that we talked about last week in lecture?
Converting NFAs to DFAs.
Yeah, these NFA things. So, what is an NFA? Yeah, these non-deterministic things, yeah. So, non-deterministic, spell, non-deterministic finite automata. So I get the deterministic part, but what do you think? What does the non-deterministic have to do with it? Choice. Yeah, this choice stuff, right? Whereas in DFA, we only had one thing we could possibly do, and non-deterministic, we have more than one choice, possibly, or 0 choices. So what are the types of choices that we could have in an NFA? Yeah, these epsilon transitions, right? So what these are we don't read anything if we choose to use this transition. We don't have to use this transition, but we can if we want to. And if we do, then we're not reading anything on the off the input. Also, another type of choice that we can have. Is there any other choice that we can have?
Choose that a certain input does nothing.
Oh, well, not does nothing.
But it stays in the same state, so it's basically dead in that state until it gets an input that recommend.
Yeah, well, let's look at this example. What about Q2 on input B? It looks like it can go to 2 different places, right? Is that a choice? Yeah, so I can have multiple transitions on the same symbol. So, multiple transitions on same symbol. All right? So these are the main differences between NFAs and DFAs. So obviously, oh, another thing. How does an NFA make that choice? Like if it's presented with these choices, how does it choose from? The way non-determinism works is, if there is a choice to be made, it will make the choice, or a choice, such that if there is a way to accept, that choice can be made there. So, for example here, if we're in Q2 and we see a B, I have a choice of staying in Q2 or going to Q1. If that B was the last character of the string, I'm going to choose this one, right? Because that transition will cause me to accept, because there is a way to accept in that case. So that's the way non-determinism works. But we can't implement non-determinism because we don't have a way of looking at the future. I wish, but we don't have a way of looking at the future and making a decision about it. So why are we even studying NFAs? Just to bore you all, or what? Why do we want to study NFAs? Yeah, they're easier to read, but is there any, because in principle I can just make a larger DFA, but why do we even care about NFAs? Was there something that it gave us really easily that it was hard for a DFA to do? Maybe something about these closure properties? Yeah, concatenation, right? We realized that if we wanted concatenation of two languages, that we needed somehow to guess when we were done in the first language, then transition over to the second one. So that seems it was hard for DFAs, but because of these epsilon transitions and guessing, we can do it very easily for for NFAs. What was another one that was much easier for NFAs? Something related to concatenation. Oh, yeah, the star operation, right? Arbitrarily choosing how many times you want to read some string out of the language and put them together. Oh, okay. So we have those two operations, and we were able to show that if you have an NFA for, in the case of concatenation, if you have an NFA for both pieces, you have an NFA for both. But what does this really tell us? It only tells us something about NFAs. Can I say something about DFAs with these operations? Oh, that was the major other thing that we saw. We were able to convert an NFA into a DFA. So now I can confidently say that the regular languages are closed into concatenation at star, because I can convert them to a DFA. It was so much easier in the NFA world, but we can convert them over. Okay? So that was the main motivation for studying this. So let's go over how we were able to do this transformation from NFA to DFA. So let's suppose I have this NFA, I'm going to give it a 5 tuple, Q, sigma, delta, Q0F. And I want some DFA produced out of it. We call it Q prime, same alphabet, different transition, different start, state, different set of final states. Okay? So now I just got to figure out, how do I define these 5 pieces in terms of the original NFA? So, how do I define the set of states in the DFA in terms of the NFA? Well, let's think about it. So, let's just look at this particular case, this multiple transitions on the same symbol. So, I have some state, and it has multiple transitions on the same symbol to other states. And I want a DFA out of this. Can a DFA have multiple transitions on the same symbol? No. So what I want to do here is I want to squash these down into one state of a DFA somehow, right? So let's just say I call this Q1, Q2, Q3. Well, a DFA doesn't have any choice, obviously. So I gotta basically put all possible choices down to one state that I can make in one transition. So I'm currently only in one state right now. I'm in the state Q1. I may be possibly in many states, but let's just say I'm only in one now. Then I better, on a transition to A, I can go to 2 or 3, but let's just model both of those at the same state. So I'm going to model both as the same state in the DFA. So in the DFA, I could be in Q2 or Q3 here, because I really can be in both of them if I read it in the NFA. So how do I model this in terms of the NFA here?
Set of ordered pairs.
It's not quite ordered pairs. Well, if this, I may be in all of the states at the same time, or in none of the states at the same time. So what is the set of all subsets? Power set, right? So let's use the power set of Q. The set of the set of states in the NFA. Now these states of the DFA are going to represent sets of states in the NFA. So as here, I'm going to have a state called Q2, Q3, the set containing Q2, Q3, which represented a set of states in the NFA. But I don't want to bar any possibility of some states being left out because I want this to not be, I don't have to be clever about this. I want this to be algorithmic. So I want every possible subset because that's perfectly fine. Okay? Let's look at the start state for now. So how do I define what the start state of the DFA is going to be? Remember, what are the states of the DFA representing in the NFAs? What are they representing? Sets of states, right? So I better write down a set over here, right? Because it's representing a set of states. So I better write down a set. Well, what set would be good for the start state?
Set of start states?
The start state of the NFA. That seems perfectly logical, right? So I'm going to have the start state. But is this the whole story? Ooh, what if I forgot? Oh, but remember in a DFA, I can't have epsilon transitions, but in the NFA I can. So I may have a situation where I have the start state Q0, and it has epsilon transitions going out to different places. So I've got to somehow include those in the start state of this DFA that I'm making. So how do I include that? Something to do with epsilon. And close it. Epsilon closure, right? So what does that mean? It says whatever set that we are currently in this case it happens to be just Q0, find out everywhere you can reach via epsilon transitions only, and then put them all as a single state. Okay? So I really want the epsilon closure of Q0. So in this case, if it happened to be, it went to Q1 and Q2, then what is the epsilon closure of the start state Q0? Well, it's everywhere I can reach via 0 or more epsilon transitions. So where can I go in 0 or more epsilon transitions? Well, I can reach Q0 in 0, right? I'm already there, so I better include that. Where else can I go? Q1 and Q2, right? Because in Q0, I got to figure out where I can go via epsilon transitions. Good. So I include those. And any other ones that those reach. Good so far? Okay. So let's figure out what the transition function does. So let's look at delta prime. Remember, what does a DFA take as input, DFA or NFA, take as input for its transition function? Well, it takes a state and an input symbol. In the case of a DFA here, it outputs a state. What do the states of this DFA represent in the NFA? Sets of states, remember? So the state here better represent a set of states in the NFA. And let's say I'm reading the symbol A. Remember, it represents a set of states. So then now I got to figure out what set of states of the NFA am I going to go to, or what state am I going in the DFA. So to motivate this, let's look at this example very quickly. So let's say I'm in the state Q1, Q2. Remember, because I can begin a set of states of the NFA here. So how do I find out where I go on input, say, A? How would I find that out? Okay, well, let's look at the transition diagram. I think a sensible strategy is if I happen to be in Q1, then I figure out, okay, where can I go on input A from Q1? Well, where can I go on A from Q1? I can only go to Q0. So I'm going to write down Q0. Where can I go from Q2 on input A? I can only go to Q1. So this is the set of states that I can reach. Right? From this set of states, I can reach this set of states. So this is the transition I'm going to make in the DFA, right? Because the DFA represents sets of states in the NFA. So this set of states goes to this set of states. Okay, well, this is an arbitrary set. I have one example that works, but how do I do an arbitrary set? Well, let's think. What I did here is I looked at every single one of the elements in here, and I decided, where do you go in the NFA? And then I looked at the second one, where do you go in the NFA? And then what did I do with all those results? I put them all together. And how do I put results together in here? What is the NFA's transition function output? A set of states, remember? So how do I put a bunch of sets together? Union, right. Yeah, so I better write a giant union over every single element in this set S. So that's what I'm going to do. So I'm going to write a union over every single element in S. So I'm going to call it little q in S. Okay? Then I got to figure out, what does this little q do in the NFA? Well, how do I find out what this little q does in the NFA? Oh, I look in the transition function of the NFA, right? What symbol am I going to read? Oh, this A right here, right? The alphabet's got to be the same, right? It has to have the same language. So I'm going to look in the transition function of the NFA on the particular state, reading that symbol. Okay? Is this all there is? You know there isn't because I asked it that way. What if I forgot? Well, I forgot final states, but what about the transition function? Is there something I forgot? Yeah, something about epsilon, right? What if I had this? I had an epsilon transition to a Q4 over here. And so I read this one character, but I could also take that epsilon transition if I wanted to. Oh, so how do I remedy that? Epsilon closure. Right? Same thing as the start state, but applied to every single transition. Okay? Good so far? Yeah.
So when we specifically say epsilon closure, we're talking about just including all states from our current state that can be reached by epsilon closure.
Well, remember that this is a set of states in the NFA, and then I just figured out where else can I possibly go, and I added to that. So, any other questions? As was pointed out to me, I forgot to set up my. Oh, go ahead.
What's S again?
It's just some arbitrary state of the DFA, but remember, it represents a set of states in the NFA. It's just a state of the DFA. I'm defining the transition function of the DFA here.
Saying that there is a state.
Yeah, I'm calling this particular state S. Yeah, it's just one of the states of the DFA I'm going to make. We'll see examples, don't worry. All right, but as was pointed out to me, I forgot the set of final states, so let's define the set of final states. Well, again, let's try to look at our picture right here. So how would I determine whether these states are going to be final or not? Well, let's think. What does this set represent? It means there is a way to get to Q1, and there's a way to get to Q2. There are ways to do that. So how do I determine that this state would be final or not?
If one of those two is final?
If one of those two, in this case, was final, right? Because non-determinism says, if there is a way to accept, it will make that choice. Or if there are a bunch of choices, it will make a choice in that way. So there is a way to get to Q1, which it happens to be final state. So I'm going to make this state final, and this one final, because there is a way to get to Q1 also. What about the state Q0, Q2? Should I make that state final? No, because none of the states in here are final. So let's figure out how to do this in general. So I want to look at every single subset of the states of the NFA, sorry. And I want to check, does it have anything in common with the set of final states? If it does, I want to make that state of the DFA final state. So I'm going to look at every single subset of the set of states of the NFA. So remember, the states of the DFA are sets of states in the NFA. So X really is a state of the DFA, but it represents a set of states in the NFA. So how do I determine if this subset X has any final states in it of the NFA? Well, how did we check that here? The final states right here was the set just containing Q1. Well, how did I determine if this set and this set have anything in common? Intersection. And then what do I check against that intersection? Well, how do I determine if there's anything in common between two sets? Look at their intersection, and then check, is that intersection empty or not? If it's not empty, then there is something in common between this subset and the set of final states. And so I should make that a final state. So what I want, oh, this should be F prime, sorry. So X intersect F, the set of final states of the NFA, is not empty. Okay? I want something in common between this subset and the set of final states in the NFA. Okay? Any questions about that? Yeah.
Sorry, so what's X?
It takes on two roles. It's an arbitrary state of the DFA, but that means it's an arbitrary set of states of the NFA. It's just some subset.
And after the Q, that continues, or is that?
Yeah, the colon, I didn't have enough room on the lines. Yeah. Yeah, it's just that there's something in common with F. Any questions about this? All right, so I think we should start doing some of the examples, the problems. So, first problem says, show that L, this language, which is the set of all strings in 0, 1 star, such that W is the concatenation of X and Y, such that X contains the substring 0, 0, and Y starts with this string 1, 0, 1. Okay? So let's think. What would be a good strategy for accomplishing this? How would I go about doing this? Is there something that jumps out to you as being somewhat important? Well, and, yeah, but is there something else that's even more important? Oh yeah, this concatenation right here, right? So, what do you think I can do? Could I just make a DFA or NFA for the first part, and a DFA or NFA for the second part, and then somehow glue them together? Oh, yeah, that's just concatenation, and we showed that NFAs can do concatenation. And so therefore, since it's equivalent to a DFA, we know that this can be made regular if I can make both the original parts. Okay, so can I make, sorry, can I make a DFA or NFA for contains 0, 0 as a substring? Yeah, how would I do that? Well, let's see. So let's suppose I have some arbitrary string, and it contains 0, 0 in it. Does it matter what happens before the 0, 0 happens? No, I don't care. What about after? I don't care either. So maybe we can just say, just keep reading until you guess to see the 0, 0. And then after that, just keep reading the rest of the string. Could we do that? That seems reasonable. So let's do that with an NFA. So what we're going to do is have a start state. And we're just going to keep reading characters over and over. So we'll self-loop on 0, 1. And then we're going to non-deterministically guess, because it's an NFA, to transition to start reading the 0, 0. Right? So I'm going to non-deterministically guess. Let's start reading the 0, 0 here. And then once I read this 0, 0, what happens? It's the final state. And then, is this all there is? Is there something I forgot?
Loop on itself?
I better loop on myself, right? Because, first of all, what is this NFA as is? What's its language? It ends with 0, 0. Because I better not have a transition, once I end with 0, 0, I better not have a transition out here. But I want to recognize strings that do have stuff afterward. So I better loop on myself. And that really does get me what I want. Okay? All right, so let's do the second one. Y starts with 1, 0, 1. So how can I do that one?
DFA?
Maybe I can do a DFA, or could I do it with an NFA? Sure, they're equivalent. So how would I do it with an NFA? I can do a 4-state that's somewhat similar to this. So how can I modify this example to work with the one I want? Yeah. I better remove this loop, right? Because I don't want anything before this 1, 0, 1 bit. So I'm going to call this Q3, Q4, Q5, Q6. I better read a 1 straight off the bat, 0 right after, 1 right after. Oh, then what do I do at Q6? I better loop, yeah. And I also better accept, because once I read 1, 0, 1, I don't care what happens after. Okay? So now, how do I glue these two together? Via concatenation. Ooh, yeah, these epsilon transitions, right? So what is concatenation? It means that the first part of the string is accepted by the first machine. Then the second machine accepts the rest of the string. So how do I check when to transition over? I guess, right? And how do I guess? I do it via an epsilon transition. Okay. I just guess over there. Is this right? What was it?
Swap, shouldn't it? Because it needs to start with the 101 and then complete the 0, 0?
No, the X is the first part.
Oh.
Yeah, but is this all there is?
And so I mean, clearly we can't have a start state on Q3, so we're erasing that and then after.
Yeah. Yeah, but is this the whole thing? Have I forgotten something? I better not make Q2 a final state, right? I claim that no string will ever get to Q3. And why is that? Because once I get to here, if I have a way to accept, I'm going to follow that transition. I can just stay right here and loop forever and accept no matter what. So I better remove this from being a final state. And now I really do get what I want, because the only way to accept now is if some way got to me to the old final state of the first machine, then I non-deterministically guess over to the second one, and then I read the rest of the string over here. So I really do get what I want. Any questions on this? Yeah.
The second machine was an NFA because you didn't have any transition, zero transition on Q3. The logic.
Yeah, because I don't, because it's an NFA, I don't care about the I don't care about the transitions not here. If I converted it to a DFA, yes, I would care, yes, but I'm not converting it here. Any other questions? Okay, so let's do the second one. it says construct an NFA for L star where L was the language up there. And we said that regular languages are close to star, so I hope I better be able to do this. So how do I do this? Well, let's look at a general case, because it seems easier. So let's say I have some DFA right here. And let's just say it has two final states. Then how do I recognize the star of whatever language this is? Well, remember, I gotta be able to go through the machine as many times as I like. So what's a sensible strategy? Yeah, so it seems like I gotta be able to come back to the start state, right? But there's a problem with that. Anyone see the problem? Problem is, what string has to be in the star of any language? The empty string, right? The empty string has to be in the star of any language. So that must mean that this start state is a final state. I better make it final. But the problem is, if this was a DFA before, I may accept a string that I didn't intend to before. Like in this case, the string AA, I didn't intend to accept before, but now I accept, right? So that's a problem. So I can't just blindly come back to the start state. But I do need to come back through the machine as many times as I like. So what do you think would be a good idea then? Something, I was thinking epsilon transition back to here, but that clearly doesn't work. But I do need epsilon transition somewhere. So where do I go instead? Oh, I better make a new start state, right? And what do I do with this start state? Epsilon transition to the old start state, because I want to be able to begin here without having read a single character. So I better be able to come back into here easily. But how do I come back over to here? I better come back via epsilon transitions. Right? Same thing as before. But is that the whole story? Have I forgotten anything?
Need to accept that.
Yes. Good. Someone's paying attention. I better make this state a final state. Why is that? Epsilon is in the star of any language, so I better accept there. Any questions about this? So let's use that here. So how do I make the star of this language from this NFA? I better make a new start state, right? Better make a new start state. I'm going to call it QS. Better make it final too, because it was final here. Epsilon transition in to the old start state. Is that it? Oh yeah, I need that looping behavior from every final state back to this new start state. Good. So I need a long transition back to there. Okay? Are we good with this? Or at least semi-decent? It's just gluing pieces together and then just barely modifying the machine to get exactly what we want. Okay. So let's actually start converting NFAs to DFAs. So I have this NFA right here. It has 3 states. And I want to make a DFA for it. Is there something that is not present in this DFA, this NFA that makes this a lot easier? Oh, epsilon transitions, right? So we don't even have to worry about these epsilon closure stuff. So that's definitely helpful. So now I gotta figure out, okay, what set of states am I currently in? So at the start, what set of states can I possibly be in? I could be definitely in Q0. So definitely in Q0. Can I go anywhere else without having read anything? No, there are no epsilon transitions. So this is the only set of states that I can go to, so I make this a state. Okay? Now I gotta figure out, since it's a DFA, where I can go on input A and where I can go on input B. So, where can I go from Q0 on input A? I can go down to Q2, and I can't go anywhere else. I may be able to go somewhere else, but I can't here. So on input A, I can go to Q2. Q0 on input B, where can I go?
Q1.
I can go to Q1 and nowhere else. And I don't have that state yet, so I'm going to make a state Q1. Okay? Q2 on input A. Where can I go on input A from Q2?
Q1.
I can only go to Q1, right? So, and I already have that state, so I'm going to come over here. Now it's where it gets interesting. Q2 on input B, where can I go? Q1 or Q2. So I gotta make a state set containing Q1, Q2. So set containing Q1, Q2. On input B. Okay. Q1 on input A, where can I go? Yeah, I can only go back to Q0. And I have that state already, so I'm going to come back here. Q1 on input B. I can't get anywhere. So what should that state be? Empty set, right? Is empty set a perfectly good set? Yeah. Why not? So I'm going to come down to here. I'm going to call the state empty set. And I'm going to go there on input B. What do you think the empty set state does? I'm currently nowhere, and I read an A. Where can I go? I think nowhere, right? So I think the same is true for input B also. So that's definitely helpful. All right, Q1, Q2 on input A, where can I go? So how's this going to work? I figure out, where can I go from Q1 on input A? Well, I can go to Q0, so I'm going to write that down. And Q2 on input A, I can go to Q1. So I'm going to go to the state Q0, Q1 on input A. Q1, Q2 on input B, where can I go? Where can Q1 take me on input B? Empty set. So I'm currently nowhere. Where does Q2 take me? Q1 and Q2, right? Because there are two B transitions. So where can I go in total? Q1, Q2. Oh, I have that state already. So I'm going to solve it. Okay. Q0, Q1. Where can I go on input A? Where does Q0 take me on input A? Q2. Q1 on A goes to Q0. And I don't have that state yet, so I'm going to make a new state. There on input A. What about input B? Where does Q0 take me on B?
Q1.
It takes me to Q1. Where does Q1 take me on B? Empty set, so nowhere. Where can I go in total? Just Q1. And I have that state already, so I'm going to go get close. Q0, Q2 on input A. Where does Q0 take me on input A? I think it goes down to Q2. Where does Q2 take me on A? Goes to Q1. Do I have a state called Q1, Q2? Yes, I do. So I'm going to come back here. Where does Q02 take me on B? Where does Q0 go on B? It goes to Q1. Where does Q2 take me on B? Well, itself and Q1. Oh, I already have Q1 written. So I go to Q1 and Q2. Oh, and I have that state already. So I'm going to add that. And I don't see any unfilled transitions, so am I done?
Final state.
Final state. All right. So how do I determine if any one of these is a final state?
It's Q1.
If any of them include Q1. So that doesn't include Q1. Oh, this is Q1. That's final. Doesn't include it. Doesn't include it. Oh, this includes it. This includes it. And that does not include it. That's pretty cool. Any questions on this? Yeah.
When you talk about Q1, Q2 state, instead of going to empty set, is that because one of them could go to empty set, but the other one doesn't, so you go to the one that...
Remember, we're doing a union over of the results that we have. So anything union the empty set, I think it's still the anything. Yeah. Yeah. So whenever you union with an empty set, you get whatever you had. But if you have a bunch of empty sets union together, they're still the empty set. Yeah.
So technically, all the states should be like the power set of Q.
Yes. That's the formal way. I'm doing it in an easier way where I'm only building the necessary states. So what state is missing from here? Q0, Q1, Q2, right? The state that has all three sets of the states here. But what I've determined is that that state is not reachable from the start state, right? And so that I don't have to include that if I don't want to. But formally, I do. But it's much easier to do it this way. Okay? Yeah.
So is the set Q1, Q2 the same as the set Q2, Q1?
Yeah, the ordering is not important. Remember, it's a bunch of unique elements, so it doesn't matter the order. Any other questions? Okay, so I definitely won't have enough time to finish this one, but let's at least start it. So I have another NFA. I want to convert it to a DFA. And this time, I really do have an epsilon transition in the middle, so I really do need to worry about epsilon closure and all that. So let's start from the beginning. How do I find what the start state is of the DFA that I'm going to make? Well, it better include Q0, because that's the start state up here. Can I get to anywhere else via only epsilon transitions? No, I don't think so, because there are no other epsilon transitions coming out of it. So this really is my new start state. Okay. So now I just got to figure out where it goes on input B and A. So just remember that this will have a lot more states, so just make a little bit of room for it. All right, where does Q0 take me on input B? Well, it takes it to itself and to Q1. I don't have that state yet, so I'm going to write down Q0, Q1. Goes around B. So this one's a little bit more interesting. Q0 on input A, where can I go? Q0 on A. Q2.
Q3.
Q3?
Yeah.
Where can I get to on input A? Can I get to Q3 on input A from Q0? No. So what am I going to do? I'm going to write down where I can get to first, then do the epsilon closure. Okay? Well, look at what we did here. We looked at where you can go on the particular input A, then we did epsilon closure. So that's another common mistake students make, is that they reverse the order here. They do epsilon closure first, then they do a character. And that doesn't actually work in general. You have to do a character first, then do epsilon closure. Well, here, I can't get anywhere else on A from Q0. So what's the epsilon closure of Q2? Well, itself and Q3, right? Because I figure out from Q2 where I can go via only epsilon transitions. Well, it's either myself, because I don't have to read one, or I can go to Q3 as well. So I'm going to make a state called Q2, Q3. And get to there on it. All right, let's start building this thing. Let's do Q0, Q1. So where can Q0, Q1 take me on input B? Well, let's see. Where does Q0 take me on input B? Well, Q0 or Q1. So Q0, Q1. Where does Q1 take me on input B? Set. So I think I better go to this state. Oh, I have that state already. So I'm just going to self-loop. All right. Q0, Q1 on input A. Where does Q0 take me on A? I think it takes me to Q2. So I'm going to write that down. Q1 on A. Where does that take me? Q0. So I'm going to go there. What's the epsilon closure of Q0, Q2?
Q3.
It's not just Q3, it's those two also, right? The epsilon closure always includes the set that you're looking at. It may include more, but it includes at least that. But I do include Q3 in here as well. So I think I'm doing A for this one. Q2, Q3. Where can I go on input B from Q2, Q3? So where can I go from Q2 on input B? I can go to Q4 and Q1, I think. Right, because Q2 is a transition on B to Q1. So I have Q1 and Q4 definitely in there. Where does Q3 go on input B? Itself. Good. What's the epsilon closure of Q1, Q3, Q4? Can I get anywhere else via epsilon transitions? Nope. So it's just these three states. And this comes on input B. Let's do on A. Where does Q2, Q3 go on A? So where does Q2 take me on A? Q1 and Q2. Q2. Where does Q3 take me on A? Q4. What is the epsilon closure of 1, 2, 4?
Includes Q3.
Q3 as including it, including these three. So it's those four states, and I don't have that state yet. So I'm going to make a state Q1, Q2, Q3, Q4. That is. All right. It's a lot easier to use an automated program to do this, huh? Right. But do you see the core idea here? In that you're just saying, okay, from here, where can I get to on a single symbol? Where can I get to here on a single symbol? Okay. Let's do one more, and then we can finish up with final states. Let's do 1, 2, 3, 4. So where can 1, 2, 3, 4 take me on input A? Well, where can 1 take me on A? Take me to Q0. Q2 on A? Well, 1 and 2. Q1, Q2. Q3 on A? Q4? Q4 on A? I don't think anywhere. What's the epsilon closure of 0, 1, 2, 4? 0, yeah, all of them. 0, 1, 2, 3, 4. Good. So we'll make all of those. Let's see this big. Should have left me around, but. And then let's do the last one. 1, 2, 3, 4, and input B. Where does 1 take me on B? Nowhere. 2 on B, where does it take me? 1 and 4, so I write down Q1 and Q4. Where does 3 take me on B? 2, 3. Q4 on B? Nowhere. What's the epsilon closure of 1, 4, 3?
1, 4, 3.
Itself, and I have that state already. So I come back. Any questions about how we were able to do that? And obviously this is not finished, but I invite you to close up everything here. So, let's just say that this were done. Let's just say it. Have I forgotten anything? Final state. So, how do I determine if anything's a final state here? If there's a 0 or a 4 in it. So, I think this one has a 0, this has a 0, this has a 0. This doesn't have anything. This has a 4. This has a 4. This has a 4. Okay? Any questions about any of this? All right, I'll see you next week.